The first talk of today's session is by Julien Roussillon from Helsinki, who will talk about degenerate conformal blocks for the W3 algebra at C equals 2 and Specht polynomials. So, Julien, the floor is yours.
Yeah, thank you very much, Ariane, for the introduction and the invitation. So today, mostly, I will talk about. Can you hear me first? Okay. I will talk about some recent work with Augustin Lafay, who is also a postdoc with me in Aalto. So it's actually in Espoo, which is really close to Helsinki. And I will also maybe mention a few upcoming results with Augustin as well, and Evelina Peltola. And so, as the title of the section suggests, which is integrability of conformal blocks, I will talk about, well, some classes of conformal blocks, and by integrability I will mean that I will mean exactly solvable, because in general these objects are complicated and not so well understood, but I will describe a class of such blocks where we can write very simple formulas actually in terms of this famous objects, Specht polynomials. So, but why I cannot I cannot move. Okay. So yeah, roughly there will be three parts in my talk. So okay, a general introduction, and then section 2 will be mostly some known stuff, but with a bit of a few new results also, but mostly the new things will come in section 3. And so yeah, I will introduce classes of conformal blocks that satisfy certain equations that are traditionally called BPZ, or Belavin-Poljakov-Samolojikov, and then I will discuss some of their solutions and some applications also. But let's start with some introduction. Well, so conformal field theories are quantum field theories with extra symmetries, namely the local conformal transformations. And in 2 dimensions, something special happens because any such transformation is holomorphic. So you get an infinite dimensional algebra of symmetries, which is called the Virasoro. And well, over the past few decades, there have been several definitions of what a CFT is, and they should be somehow equivalent to each other, which is not obvious at all. But let's say the first one is kind of the traditional approach to QFT, which we call a path integral formulation. And then the second one is kind of geometric. It's a geometric axiomatization by Segal around 1988. And the last one was developed by physicists Belavin-Poljakov-Samolojikov in the very famous paper of 84. And it goes by the name of conformal bootstrap. So in this talk, I will mostly rely on this approach, conformal bootstrap, because it's actually quite powerful to make new predictions, let's say. So let me. Oh yeah, before I wanted to say that very recently there have been a lot of work, rigorous work in the case of the Liouville conformal field theory, and in a very impressive series of work, people showed that all these 3 approaches are consistent and agree with each other, and they have been rigorously implemented. So here I wrote a list of papers, which is a list of people, which is not exhaustive, of course. It's been a quite active field with many papers, and many people have contributed. But okay, now let me briefly talk about the conformal bootstrap. So it's kind of an axiomative and recursive method to construct correlation functions in general. And what comes out of the conformal bootstrap in general is that the correlation functions split into two parts. First, we have some quantities that depend on the model, and usually they're called structure constants. And the other part are universal quantities, which are fixed by conformal invariants, and they are called conformal blocks. So there are different approaches to what conformal blocks is. For example, you can, if you're more into geometry, you can there is some geometric formulation of conformal blocks. But if you're not into geometry like me, for example, you might think of these objects as just special functions which are determined by representation theory of Virasoro. So in general, these objects are, I mean, there are many kinds of conformal blocks, and in general, they are not so well understood. But there exist special cases where actually both correlation function in general and conformal blocks satisfy a system of PDEs that I will call Virasoro BPZ. And so here I say BPZ because it was really Belavin, Polyakov, Zamolodchikov with their methods who were able to predict such equations. And arguably, maybe the simplest example occurs when conformal blocks become hypergeometric functions, some well-known classical functions, special functions. And okay, as I just said, yeah, this conformal bootstrap approach gives a nice approach to derive the PDEs. And this is actually what I will describe a bit this a bit more later. Well, now actually, I will move to this now. So I will introduce some, talk about BPZ equations in general, and then introduce a special class of them, which have some nice applications, especially in critical lattice models. And I will discuss some of their solutions in terms of some Specht polynomials. Okay, so let me start. So here there will be a bit of algebra to derive the BPZ equations. And so here I recall the definition of what the Virasoro algebra is. And it's generated by this ln which satisfy these commutation relations. And then C is the central charge, basically. And the very important objects in this approach are the Vama modules. They are labeled by C, the central charge, and the parameter H that, let's say in physics, we call conformal dimension. And these modules are generated by the so-called highest weight vectors, V0, which satisfy some conditions. And especially, there are eigenvectors of L0, which eigenvalue H, and they are killed by the positive modes. And then the Vama module has basis. So you apply all the negative modes onto V0, basically. That's how you get all the vectors in the module. And so an important number is called the level. So if you take the basis element L minus N1 up to L minus NP V0, so you can define the level, which is the sum of all the Ni's. And in particular, any element of level N will be an eigenvector of L0, which with a shifted eigenvalue H plus N. And well, one of the simplest examples we can think of is at level 2, we can have L minus 2 V0 and L minus 1 squared V0. And well, it's a very simple exercise to apply L0 there on the left. And then using the commutation relations of Virasoro, we can get this this with N equal 2. And so now I can say what a singular vector is Wn, well, simply it will be a highest weight vector at a positive level. So positive level, and so it should be killed by the positive modes of L. And so if you can find such a vector, the Gamma module is said to be degenerate, and this vector Wn will generate a proper sum module. So in the literature, there are existence results, and in particular, we can find singular vectors at level R times S whenever this H takes some. So okay, I don't write the general formula, but there is a formula that depends on R and S, and so this is called the catch table when this parameters H lies in the catch table. And so let's probably the simplest non-trivial example arises when we at level 2. And so here I wrote a certain parameterization for the central charge. This might look a bit weird to you, but if you haven't seen this formula, but so there are a lot of things are usually parameterized by this. So this is why I use this notation. And so if we parameterize the central charge in this way, there are two singular vectors at level 2. Namely, we will have h12, h21, and then the singular vector, I'll say, it will be some linear combination of n-2 and n-1 square applied to V0. And actually, there is some duality relating the two guys. If you exchange kappa and kappa over 4. And yeah, I just want to say maybe that there is also another famous parameterization, it's called Liouville type parameterization, where generally instead of kappa, we have a small b, and then we will have a duality b becomes 1 over b. But here I use kappa. And so, okay, from this business of singular vector, with a few extra ingredients, BPZ managed to predict a certain kind of PDEs. So here I will not describe the details, but I would just like to give the idea. And the idea is that in this conformal bootstrap approach, there is you can associate a vector in an irreducible Virasoro Gamma module and local fields. And so I described the highest weight vectors before. So to each highest weight vector, you can associate a primary field. But then if you have a degenerate Gamma module, so if you can find a singular vector, then the corresponding highest weight vector will be called the degenerate field. And then the singular vector in the degenerate Gamma module will be called the null field or zero field. And yeah.
Sorry. So what is the difference in this classification between degenerate fields and null fields? Maybe I missed something.
Oh, so I think in the example, probably I can write it here. So can you see my mouse moving or?
Yeah.
I don't know. Yeah, so V0 here, for example, will be the degenerate field.
Mm-hmm.
So the highest weight in the module that has eigenvalue h21 with respect to a0. But then the null field will be this whole thing, w21.
Okay.
It will be the singular vector. Yeah.
Okay, thank you.
Yeah. So yeah, so the first thing is that PPZ say, okay, if you have a correlation function with a null field inside, then you get 0. So this is the first ingredient. The second ingredient is that using the so-called conformal word identities, you can show that correlation functions of dissonant fields. I think I didn't define what a dissonant field is, but dissonant field is that, let's say you take a V0 and then you apply any negative mode on it. So N-1 V0 or N-2 V0. So this would be a dissonant field. So correlation functions of dissonant are given by some differential operators acting on the correlation of the corresponding primary. And so this is essentially how they concluded that correlation functions of degenerate field must satisfy some PDEs. So I have to say two things. I will give a bit more concrete example in the next slide. And the second thing is that it might look kind of like a magic box if you're not into this field. But so there is, I'm talking about the physicist approach here, which is of course not rigorous. But most of what I'm talking about right now, actually, it has been made rigorous in the context of dual CFT. So this is pretty nice. But here, for simplicity, I just use the physicist approach. So here, this is a more concrete example of what I was just saying before. On the left-hand side here, so what are this VH of Z? Let's say it's a primary field in some CFT, and then this will correspond to a dissonant in algebraically. And so the correlation function of this guy is given by some differential operator acting on the correlation of the primaries. And so if you insert a null field, so see, if you remember, this is just V0, some V0. So this is some singular vector if you think about algebraic part. So if you insert a null field, okay, BPZ tell you that this must be 0. The left-hand side here is 0. But on the other hand, we know that this N-1, N-2 act as by some differential operator. So you get some PDE at the end. And yes, and in the simplest non-trivial example where we have three generic fields and one null field here, they showed that this is essentially equivalent to the hypergeometric equation. So this is pretty nice. And okay, so now you can cook a lot of different BPZ equations because here, for example, I put only something at level singular vector at level 2, but then you could put something at level R times S, so you can really cook up an infinite amount of BPZ equations and various kinds of equations.
I have just one question
yeah.
about the operator Li. Other than the algebraic rules that it should, okay, it is constructed by algebraic rules. Is there another way to express them? Just to understand if their definition is just by the algebraic rules, or we can explicitly express them otherwise. I don't know if my question is has meaning. Okay.
Okay, I'm not completely sure, but well, let's say in the physics approach, these modes, Virasoro modes Ln, are closely related to the stress energy tensor of the CFT. So I don't know if this would answer your question, but
so we cannot view them as some written by ordinary differential operators, or so each time we should go back to the algebraic rules to deduce their properties. I'm coming from the mathematics side, so maybe I don't understand physics of it. So
yeah, it must be not so clear at all. I'm not completely sure I understand the question, but I guess what we should understand here is that on the left-hand side you have a certain correlation function, and here another one, and these two must be related by some differential operators that.
Okay, but we don't know what is it explicitly. We just use the I mean, usually just the algebraic properties to.
But what is explicitly? You mean what this Ln are explicitly, or you mean what this whole thing is?
Yes, the Ln. The Ln.
Maybe
can I quickly interject?
Go ahead.
is the question that how do you know what kind of differential operator you need on the right hand side?
Yes, in some sense, yes.
Yeah. So I think the point is, okay, you have this L minus n, but how do you know that L minus n is this 1 over Z minus Zn stuff?
Yes, okay. So okay, I'm trying to, because in the beginning we had some algebraic. The Ln is we just know how they behave in some sense in some algebraic rules with the commutators.
So
now
I might have a remark, but maybe you already are aware of this, Ayman, but it's so usually when you work in CFT, like these are like things that there are some things that are true whatever the precise theory you're looking at, like that you have a representation of this Virasoro algebra, and then the game is to have like some sort of explicit or some characterization of, for instance, your correlation functions. And I think that it's not like, for instance, the operators Ln, like you don't have a complete information on them when you start, and you want to determine like your correlation functions and the rest of like the specifics of a given theory, but you don't have that as a given information when you start doing the computations. Well,
okay.
Maybe Julien can add
I understand
some...
better. I understand better. Yes. Now I can see it better. So at the beginning we like axiomatic. Okay, in some sense we start by the rules and then we can deduce how they behave later in some sense, according to
and what makes the bridge between the algebraic setting and the, let's say, the analytic setting is what physicists call the word identities. But maybe from a mathematical background, maybe it would make things clearer if you open some papers from Kupiainen and I forgot how many, Vargas. So they have a paper where they kind of make this explicit, and they talk about these word identities, etc. In the context of Liouville CFT. So maybe starting from this might help.
I will check if you okay. I will ask you later for the paper.
Yeah.
I will check.
Thank
you. Thank you, and sorry for the interruption.
It's okay. It's okay. But yeah, maybe I should move on. Okay. So I forgot where I was. Okay, so this is just some discussion that these PDEs appear in many areas. And yeah, for example, they are used to construct the structure constants of Liouville CFT, this DOZZ formula. So the idea was expressed by Degenerate in the 90s. And then it has been made completely rigorous by Kupiainen, Roth, Vargas in the Annals in 17. Some of them can also be used to construct a certain class of conformal blocks. So this was written by Gozal, Remy, Sun, and Sun. Also, we have connections to isomorphismic deformations. Maybe Harini will talk about this, by the way, I assume. In the case of central charges, C equal 1 and infinity. And finally, another kind of application that might be more related to my talk is the application to the scaling limit of some critical lattice models and multiple Schramm-Lohner evolutions. So in what comes next, I will just write a special class of such equations. And for the moment, you can just forget about CFT. So you can just think about this weird black box like as a generator of some equations. It will give you some equations, and then you just want to work with the equations. This is the way I see it. So this is an example. So here I'm writing a certain set of PDEs where all the all the fields are degenerate at level 2. So it means that we have as many PDEs as points, if you wish, and all the PDEs are second order. And so, yeah, for certain reasons, it's nice to, in this case, to restrict the excess to be real. So I define this configuration space, and then we define this space of functions. So all real valued functions which satisfy this set of PDEs, and also a certain covariance property with respect to Mobius transformations. And also we require some power law bound. So we don't want them to diverge too badly or something like that. So this space of functions was studied quite a lot in the literature, especially in the context of SLE and critical lattice models. And in particular, for example, Flores and Kleban showed that the dimension of this space is 0 if n is odd, or a Catalan number if n is even. So a Catalan number, it shows that it's pretty nice because these numbers, they count all sorts of combinatorial objects. And actually, yeah, in this case, when we work with BPG equations with only degenerate fields, we get yeah, applications in some kind of in this kind of things. So here I draw two kinds of objects that are counted by Catalan numbers. So on the left side, it's I will call it planar pair partitions. So you have, let's say, the real line, and then you put a certain number of points on it, and then you connect the points in such a way that there is no crossing. So these objects are counted by Catalan numbers. And on the right, I write a standard Young tableau. So Young tableau, quite easy to define, is just a collection of boxes, and then you put numbers on it. And then a Young tableau is standard if the entries increase strictly down the columns or along the rows. Okay, so here it's a standard because I always increase when I go down or when I go to the right. And yeah, it turns out that this space of function that I defined in the slide before, in the case where kappa equals 4, it has a basis consisting of functions that are proportional to this famous Specht polynomials. So instead of writing a general definition of what a Specht polynomial is, I think it's just simpler to go through examples because it's quite intuitive. So if I take this tableau, for example, 1, 2, 3, 4, 5, 6. So I look at each column independently, 1, 2, 3, and then I form the Van der Waals determinant associated with the column. So for example, 1, 2, 3, I have x3 minus x2, 3 minus 1, 2 minus 1. And then same for the second column. So, okay, if I give you a tableau, it's very, very easy to write what the Specht polynomial is. And so,
can
yeah,
I ask
this
something?
yeah,
I have
sure.
a question. What is the starting point to define these polynomials? Why this particular Young tableau?
Well, one reason is that there are sufficiently many of them. There are exactly n over 2 Catalan number of such tableaus. But how to say? You could define let's say you could define a space which is the span of all the such functions for T, not necessarily a standard Young tableau, but any tableau you want, but you just want the shape to be 2 columns. So this one is important. You want 2 columns.
But why?
Well, I would say maybe because it's the only one that will be enumerated by the Catalan numbers. That's one reason to see it. But well, another reason, if you want to have a more brutal approach, is that it's really these guys that will satisfy the equations I wrote before. These equations, they are satisfied by these guys, and you want the tableau to have this shape. So, but I don't have a more intuitive reason for this fact. But yeah, as I said, you could define a space, a span of this UT, where T is not necessarily standard, but you can put the numbers as you want. But it turns out that the basis, it has basis where T is a standard Young tableau. So if you put any tableau, you can always write the Specht polynomial as a linear combination of Specht where the tableaus are standard.
Oh, okay. I just saw your header. And is it true that for WN algebras, you expect like n column Specht polynomials? Something
yeah,
of that
that's what we expect.
Yeah.
So
okay,
in the third section, I will describe the 3-column case. Yeah.
I see. So in some sense, this 2-column is because you're in Virasoro.
Yeah. From this point of view, yes, exactly.
Yeah. Yes. Okay. Yeah. Okay.
Yeah. And I wanted to make a comment here because this is kind of a reformulation of a previous result from Evelina Peltola and Hao Wu. So they already constructed the basis for this space, but the connection to this Specht polynomial was not obvious. So this is a rewriting of their formulas, essentially. Okay. Yeah.
I also have a question on that slide. So you said that previously there were results that gave the dimension of this space of solutions as a Catalan number, essentially. So were these results like the proofs, are they like bijective in some sense? Like they already give a relation with some combinatorial object, or is it just like calculations?
So I believe that the proof they have, it relies on the fact that the PDEs are hypoelliptic. And I think they use a lot of some, maybe if you're an expert in PDEs and hypoelliptic PDEs, but I guess that they use a lot of machinery from hypoelliptic PDEs. And so the point is that, okay, it might be completely true what I say, but I believe maybe they construct, they find a lower bound for the dimension by constructing a subspace of solutions, maybe, I assume. And then they prove an upper bound by using this machinery, this hypoellipticity property.
Okay, so there is no direct connection with like a combinatorial object counted by Catalan numbers. Yeah.
In the proof, I'm not sure, but what is nice in general is to label the basis element by this kind of object. And it turns out that for applications to lattice models, sometimes it's nice to think of basis elements as labeled by this object or this object. But in the proof of the dimensionality, I don't know enough about what it is. So, yeah.
Okay, thanks.
Yeah. So here, this is more like a bonus slide if you like algebra, because Specht polynomials were introduced actually a long time ago, maybe around 100 years ago, actually. And they were introduced to study irreducible modules of the group algebra of the symmetric group. And so using these known results, essentially, we can naturally endow the space, this space when kappa equals 4, with the structure of an irreducible module for this algebra. And we show actually in some upcoming paper that that this actually descends to a module over a famous quotient of this algebra, which is called temporally. And the parameter, let's say, it depends on some parameter Q that you can think of, maybe some quantum deformation parameter. And so in this case, it's equal to -1. But okay, I will not discuss this further. It's not the point of the talk. And then here quickly, I guess to motivate, because I guess it's nice to find some formulas for these objects. And by the way, if from a physicist point of view, you can think of any element of this space as being a conformal block. if you want. So you can think of this as an integrability result for this class of conformal blocks. But then I guess it's always interesting to know what they're used for. I mean, it would be nice to have some applications. So here is some explicit application in the context of the double dimer model. So here I draw a superpose. I mean, I don't draw. No. I took a picture from Kenyon Wilson in 2011, and so this picture represents a superposition of two dimer configurations. So how to say? The idea is to take one grid, a square grid, and then you put a random dimer configuration on it. And then you take another grid where you remove a certain prescribed set of boundary points. So in this case, 1 up to 8. So you remove this point, and then you put a random dimer configuration on this new grid. Yeah. And then you superpose the two, and you get this this figure. So you get some collection of edges, and then you see the appearance of some loops, and then you see the appearance of these black curves. And so in particular here, you see that they form multiple interfaces that form a planar link pattern. Yeah, because then you can draw it here, for example, the kind of picture that I drew before, and then you would have 1 connects to 8, 2 connects to 5, etc. And then Kenyon and Wilson showed that you can compute the probability. So if you take two random configuration, then they show that you can compute the probability of obtaining a given link pattern. And they showed more than that. Actually, they showed that it has a well-defined scaling limit. So when the mesh size tends to 0, it has a well-defined limit. And the conclusion actually is that, so it is stated quite informally, but the scaling limit of these probabilities can be expressed as a ratio f over g, where f and g actually live on this space of function that I defined previously. So in another word, you can think of the scaling limit of these probabilities as a ratio of two-column Specht polynomials, or it would be more correct to say linear combinations of ratios of linear combinations of Specht polynomials. Maybe it's more correct. So this is an explicit application. But more generally, so here I described the case kappa equals 4, but there is a similar kind of thing happening for other values of kappa. And you see, so in general, certain ratios of elements in this space for any kappa are expected to describe the scaling limit of connection probabilities, describing link patterns. And so there are results like the one I described in the case of, for example, GFF, Loop-Perez random walk, Ising, percolation, maybe other. Yeah, and then the parameter kappa here describes the universality classes, and from the CFT point of view, it parameterizes the central charge like this. So this is actually why in the section before I was parameterizing the central charge like this. It's quite standard in this field. And yeah, this space also is how to say, certain elements Z of this space are quite important from the point of view of SLE, and they are called the pure partition functions of multiple SLE. Yeah. So I will not talk about this at all, but if you know about SLE, I guess that connects, gives a connection. And so now I would like just to motivate the next section. So what we do actually with Augustin, because it originates from a paper of Kenyon and Shi, a very recent paper actually, from around Christmas of 2023. But actually, so Kenyon came in June of last year in Helsinki and gave a series of lectures about this. So So we started thinking about this thing around last year. And so, yeah, so in this paper, they study things a bit similar to the slide on the double dimer, but in the case of the triple dimer. So let's say instead of superposing two dimer configuration, you superpose 3 of them. And in this case, they study the case where you get some new kind of geometrical object formed by the multiple interfaces. And so these are no longer called planar pair partitions, but they are called the SL3 webs, or maybe it's more correct to say reduced SL3 webs. And so this is a picture taken from their paper. And so essentially you can, the novelty here is that when you have planar pair partitions, so you only have, let's say, arcs that connect boundary points. But in the case of webs, you can have some non-trivial branching in the interior of the domain. So this makes the thing actually quite more complicated. And nevertheless, they managed to prove that, I mean, they could compute probabilities of obtaining a certain reduced web in the discrete. And they also proved the convergence of the probabilities in the scaling limit. And so, well, it seems very natural to think, okay, can we generalize what I described before? Can we find some CFT interpretation of his results? And well, we conjecture that yes. And in the next section, I will introduce, what kind of objects we believe are related to their probabilities, essentially. So this brings me to the last section. Okay, I should have enough time. By the way, I should stop at what, 50 or something like that?
Yeah, I mean 55, I think.
50, okay, yeah. Okay, so here I will put my physicist hat on again. So this, for mathematicians, it will look a bit weird maybe, but I should say that what we do, we use this weird machinery of conformal bootstrap to essentially to be able to generate some equations. And then we can forget about CFT and all this stuff, and we can just focus on the equations only and find their solutions. So this is what I'm going to do. So here there will be a bit of physics and algebra again. And it will involve some generalization of Virasoro. And this story began by Samolojikov in 95, because he discovered families of CFT, which on top of the Virasoro algebra has another kind of extra symmetries that physicists sometimes call higher spin symmetries. And the resulting algebra is nowadays called the WN symmetry algebra. So algebraically, it's not a Lie algebra actually. It's an associative algebra which strictly contains Virasoro. And people understood that it arises as a Drinfeld-Sokolov reduction of the affine Lie algebra SLN. And so actually you can define a similar kind of algebra also for other kind of semi-simple algebra. But yeah, traditionally people call WN associated to SLN. And the nice thing is that the conformal bootstrap arguments that I talked about before, they also apply in this case, although it's a bit more complicated. We need a bit more ingredients. And so at the end, I will introduce a new class of conformal blocks. And so now I call W3 because it's based on W3. So now in the algebra W3, you have this Ln still, but now you have an additional set of generators Wn, where n is integer. And now it's a bit more complicated because you still have a notion of Varma modules, but the Varma modules will be parameterized by elements in the weight lattice of SL3. Yeah, so they will be parameterized by this vector alpha. But other than that, it's still very, very similar. So you still have a highest weight vector V0, which is an eigenvector of L0. But the new thing is that it's also an eigenvector of W0 with some eigenvalue rho. And then they will also be killed by the positive modes of L and W. And similarly, we can still ask about the existence of singular vectors. So we can define everything pretty much in the same way as before. So I will not go into big details. But here I will focus on a specific example that was described by Fatayev and Litvinov in 2007. So these are physicists, well-known physicists, and so the case they consider. So okay, now we parameterize the central charge in a different way in terms of a parameter beta, and then we consider two Verma modules where alpha takes these two values, I beta W1, I beta W2. And then in the paper, they define the highest weight vectors in this way. So the conformal weight will be given by this, and then the W0 eigenvalue will be this. So if you really want to think of it from a physicist point of view, so you will have two different type of fields, of local fields, of degenerate fields actually. So they will have the same conformal dimension, which will be given by this, but they will have an opposite eigenvalue for W0. Okay, they will have a different sign. Is the only difference between them. And so it turns out that the two Verma modules are degenerate, and they both contain three singular vectors. So in the next slide, I write the explicit formula for the singular vectors. Okay, so it's kind of we can verify by hand basically that these are singular vectors in the sense that they will be killed by the positive modes of L and W, etc. And so yeah, the singular vectors are of different level, if you want, level 1, 2, 3. And so yeah, there are some explicit linear combinations of the generators. Yeah, and so now it's still the same as before, just a bit more complicated because we have more generators. But you can really think of V01 and V02, the two highest weight vectors, as being associated to two different local fields, degenerate fields actually. And then the correlation functions of the corresponding null fields vanish. But on the other hand, you can also use the fact that correlations of descendant are given by some differential operators, etc., etc. So the point here that I want to make is that we can use these arguments to throw a set of equations. Okay. Actually quite complicated, a set of third order PDEs. And this is what I write next. Okay, it looks a bit disgusting, but this is the way it is. Okay, I should hurry. But yeah, now we can forget about CFT and all this conformal bootstrap machinery, etc. And this is how we start the paper, actually. We define the space of functions. Okay, so we say that we have a set of real valued functions that will satisfy all this set of third order PDEs, plus okay, a bunch of other properties. And okay, what do I want to say? It's a bit annoying here because we need to introduce a certain number of parameters. Let's say they are entirely characterized by this set of parameters. So var sigma will be given by S1 up to SD. So all this S1 up to SD, they are equal to 1 or 2 only. And then we define a parameter Q that is -1 to the power S plus 1. So, okay, you can just think of Q as being always -1 or +1. So you see here, yes, it will not be always a plus sign in front of the third order operator. So yeah, in general, it's quite quite complicated. Maybe there is a way to make it cleaner, but we don't know. And so, yeah, quite surprisingly, even though the equation look quite disgusting, we can write a really simple formulas for some solutions. And so now we focus on the case C equal to, okay, the central charge equal 2, which means beta equal 1. And okay, we don't know what the dimension of this space is. So we cannot say, okay, we construct a basis for this space. So what we do instead is that we construct a subspace of solutions. And so this is why we introduce this space C, in the case C equal 2. And so we define it to be the span of functions that are proportional to, again, the Specht polynomial, but where the tableau is a bit more complicated. So here, it means filling. You can just say a tableau, and this it will denote the content of the tableau, and this it will be the shape of the tableau. And in particular, you will have 3 columns and n divided by 3 rows. And so, yeah, it's just better to write examples. So in this case, for example, this is a filling with content. So by 2, 1, 1, 2, 2, 1, I mean, for example, the number 1 will appear twice, the number 2 will appear once, etc. Okay. So this tableau, for example, is a filling. Okay. 1 appears twice, etc., etc. And in a filling, you don't care about increasing order or decreasing, etc. But the proposition that we have is that a basis for this space is now the same functions, but T runs over the set of column strict Young tableaus. And now in a column strict tableau, you want the entry to increase down the column only. But along a row, you can only weakly increase. So for example, here you have 1, 1. So this is a column strict Young tableau. Okay, so
can I ask a question?
Yeah.
Sorry.
Yeah.
I actually don't understand how you might prove this, because the statement is about the basis and not about the conformal block, right?
So I'm not
You're
sure I
saying
understood the
that,
question. Yeah.
So the proposition is saying, this is also true for the 2-column Specht polynomials, actually. That's something that I don't think I understand, which is that the claim is that, okay, you have this DPZ equation and you have the conformal blocks. You have the dual conformal block.
Mm.
And then you're saying that these conformal blocks can be constructed using the bases, which are then given by Specht polynomials. Is this true?
Any element of this space, you can think of it as a conformal block. But the basic, so yeah, any element of this space is a conformal block actually, but just in different channels.
Okay.
But then the basis that we write,
the conformal
actually,
block itself is described in terms of Specht polynomials. Sorry for interrupting you.
Yes. And so, yeah, actually, I didn't say it, but all the bases that I wrote there, they do not correspond to the usual basis that we use in CFT. So usually we have a basis, we have this diagrammatic representation of the conformal blocks in terms of how is it called? the comb, yeah. Usually people use the comb basis for the conformal blocks, but I should say here that the basis that we write does not correspond to the comb basis, yeah. And it's not so clear to us how to relate the two bases. And so the reason why it's not a comb is that we can easily see that they are not, they do not diagonalize the monodromy matrix around certain points. So this is what we expect from the comb basis in general. But yeah, any element of this space, you can think of it as it's a conformal blocks, but just in a certain channel, if you want. Yeah. Okay. Yeah. Okay. I'm almost done. But let's say the main result of the paper is that this space C is a subspace of the space I defined before. So it means that these functions, they satisfy all the equations that I listed before, which is a priori non-trivial. And the proof is you just plug the equations and then you compute. Basically, it's a pure computation. And I want to say that a remark that the dimension of this space C is, of course, the number of tableaus, of column strict tableaus with the content var sigma and this shape. And this is given by a certain Kotzka number. And it's nice to see that this number also counts the number of reduced tree webs. So this is quite reassuring. And we actually conjecture that, yeah, actually the two spaces are the same. So what we call C, we define it to be the space of conformal blocks. Well, we expect that C and S is the space of conformal blocks. But from a pure mathematician point of view, we don't know what the dimension of S is. And we should prove an upper bound for the dimension. And yeah, looking at how the equations look, it doesn't seem easy to do. But yeah, one of the last points is that I wanted to mention that, okay, the conformal blocks I described, up to some prefactor, they are given by Specht polynomials. And so if we move the equations past the prefactor, we get equations for the Specht polynomials themselves. So in the case of Virasoro, we had second order PDEs. And so here we can deduce that any Specht polynomial where the tableau has two columns satisfy all these equations for m between 1 and n. I forgot to say. So it satisfies n PDEs. And then in a three-column case, we can also do the same, and we can see that in the case where all the content is only 1, 1, 1, 1, 1, the Specht polynomial satisfies this set of PDEs. And if you stare at the equation a little bit, two columns, three columns, well, clearly we see some kind of pattern. It looks quite symmetrical. So this led us to conjecture a case for the n columns. And yeah, we are a bit puzzled because in the literature, it seems that people have not studied Specht polynomials from this point of view. So yeah, it would be nice to investigate this further and to try to prove the conjecture. And probably it would require new tools because what we did for the two column and three column case, it was just like a pure computation. So we cannot do this for any n. And lastly, yeah, very informal statement, but we could verify for some examples that the scaling limit of probabilities that were described by Kenyon and Shi, they can actually be written in the form f over g, where f and g, essentially, they are linear combinations of these Specht polynomials. Okay, in the paper, we write a bit more precise statement for the conjecture, and we could verify it in specific examples. So yeah, it would be nice to try to prove it. And so finally, yeah, just to recall, we described the class of degenerate conformal blocks for W2, which is Virasoro, and W3. And yeah, if we look at the formulas and the structure of the formulas, it's very natural to expect that this will generalize to bigger n. And probably there will be some connections to the n-fold dimer model. And also beyond the case of C equal to, we expect that the space of functions we introduce will have scaling limits of probabilities in all sorts of lattice models, which are based on SL3 webs. But as far as I know, beyond the triple dimer, there is nothing basically in the literature. So it's quite open. And yeah, if there could be some SLE type description of SL3 webs, we expect that this third order PDEs we introduce could play an important role, just like the second order PDEs play an important role in the case of SLE. And okay, I just finished by a few references that I think are important. So okay, of course, the talk was based on this paper. And then this is the paper of Kenyon and Shi. And I think I didn't mention, but a lot of what I said about the algebraic part, the W3 and the conformal bootstrap, some of this has been made rigorous by Sarkle and Huang. In the case of SL3 Toda, which is a generalization of Liouville. And yeah, finally, this is the paper of Fatayev and Litvinov, a physics paper that we base a lot of things on. And so that's it. Yeah. Thank you for your attention.
Thank you very much.
I
Are there any
question.
questions? We already asked a few, but if there are some more, go ahead. Harini, you wanted to?
Yes, I have a very quick question. So in the Virasoro case, your kappa needed to be 4 for the Specht polynomials.
Yes, or C equal 1.
Yeah. And then for W3, it goes to kappa equals 2, or well, C equals 2.
Yeah, C equals 2, yeah. Yeah, so I don't think I have a satisfactory answer, but essentially when you add, from a CFT point of view, when you add a W, so when you have Virasoro, you have the stress energy tensor T.
Yeah.
And when you want to add extra symmetries, so you will have this this current W, and somehow they will modify the value of the central charge somehow. This is the reason why. So for Virasoro, C equal 1, W3 C equals 2, and we expect that for Wn we will have n minus C equal n minus 1. Yeah.
So for the Wn case, do you have any conjecture on what the kappa should be or what the C should be?
Yeah, n minus 1.
Sorry, I don't. N minus 1. Yeah, okay.
Yeah.
Sorry, I was just trying to make a note.
No problem.
Yeah.
No problem.
Yeah, thanks.
Yeah, it seems very natural to think this way, and we can probably write some very explicit formulas, but the problem is how to prove them. Because what we do for n equals 3 and 2, we just compute, blindly compute. We throw the formulas and we compute. Yeah, I just wanted to, here, this one, we can probably write something very similar for Wn. But yeah, we need some new tools, I think, to prove. Even to write the equations, actually. I mean, this is quite disgusting, order 3. So what is it, order 4 or 5? Yeah.
So I had a question, or I don't know if it's more of a remark, but like your results about the relation between conformal blocks and like very combinatorial objects, it made me think of works by Karen Yeats, for instance. So let me write her name.
Yeah, I'm not sure I know.
So she has like with also some collaborators, she has several works where like I think it's for very general QFTs, they relate basically Dyson-Schwinger equations with things on chord diagrams. So it's not exactly like your non-crossing diagrams, but it's kind of a related object. And so it's not within the framework of CFT, but I don't know, maybe there might be some like arguments that can be borrowed from one side to the other. I think it's, well, it looks a bit like similar in the terms of, well, I don't remember exactly how their proofs go, but I don't know, you might want to check it out.
But yeah, if you have a specific reference, it would be nice.
Okay, let's
but they have the polynomials, etc.
So they have basically formulas for Dyson-Schwinger equations. Okay, so for instance, in this article, so you can see the type of diagrams that they have, and well, I don't remember the statements of their main theorems, but it allows them to have like some result on like the behavior of some relation functions, but it's within a very general framework. But yeah.
Okay, but yeah, thanks. It's nice. I will take a look. Yeah, it's yeah. Usually the literature is so heavy, and it's nice to see that there can be something else outside CFT. Yeah. It's nice. Yeah, I see this kind of crossing this time.
Yeah.
Yeah, I didn't know that this kind of combination they correspond. Oh yeah, okay. And then the connection to Feynman diagrams, etc.
Yeah. So yeah, I mean, I'd have to read the papers again in detail to tell you what they say, but that's the spirit of yeah.
By the way, should I stop sharing, or I don't know if there are still questions?
Yeah, I don't know. Does anyone have any other question? If not, well, thank you again, Julien, for this very nice talk.